I don't know how I skipped it, but I must have. All right, so the thing about this that's actually interesting is that you can drop as many of these onto the rails as you want. Right? It can fire these as fast as you can drop them onto the rails. As long as you don't generate too much heat on the rails and melt the rails, then you can launch them one after the other. That's one reason why these are kind of interesting. Every individual one of the slugs would receive the same magnetic force. They're all being dropped in parallel, so they're all going to see the same potential difference. Your limit is based purely on whether you can maintain the potential difference in the magnetic field and the thermal degradation of the system itself. I see no reason to go over the next part. You guys should be able to figure out that the frictional force is going to be equal to mu times the normal force, which is going to be mu mg, and you can just set that in here as the amount of work done. So I don't see that as a thing that has to be done. So what's the next question? So the wire begins a distance s above the area with the magnetic field. Don't know the direction of the magnetic field. I'm not sure it matters. So I just said this is the region of space with the magnetic field. And the loop is going to make it to here with a speed equivalent to the square root of 2gs, which I will state without proof because you guys are supposed to be able to do that. So it just falls under gravity. When it reaches that point, of course, the loop is moving at that speed. What are we trying to work out here? The size of the magnetic field for this to or how much current would be, how much current would be produced. I think we're trying to indicate that the moment it enters this region, we would like the net force to be 0, so that the velocity is a constant as it enters this region. So we want mg to be equal to ISB. That would make it so that once it reached this point, it would have that speed. It would not change its speed. Is that kind of what I think that's what we're supposed to infer from the problem. What are your thoughts? I mean, that was what I was kind of inferring. Now, we needed to get some velocity to the wire by the time it reached there. We could have it accelerate, but I'm thinking if we drop it like this, then it will definitely enter the field because it's going to be traveling at a constant velocity into the field. Now, this tells us how much current we'd have to generate to do so, or what the size of the magnetic field would have to be. We also know that the EMF produced in that loop is going to be equal to BSV. Yep.
If the threshold is determined, we need to prove how we get BSV.
If it's determined, no. If it was derived, yes. But in this case, we weren't actually even asked to find out the EMF produced. That was kind of more the problem before this, right? At this point, I think we can probably start from here. And that means the current in that loop is going to be equal to BSV over R, the resistance of the loop. So, one more step. BS root of 2G. Oh, where's the S? 2GS over R. That's got to be the current we're producing. So I'm going to drop that in for current here. And mg equals BS root of 2GS over R times SB. All right, so what are we supposed to find? The size of the loop or the size of the magnetic field? Right, this is the relationship that would have to exist for the loop to travel into the region with the magnetic field at a constant velocity. So whatever it is the problem asks you to find, you can find it. I don't know if I have to do any more than that. That's just bringing all the pieces together. But is there more that you want me to go through? Now, you could change the dynamics here. I mean, you could change it so that it accelerates, slows down or speeds up. But the moment the whole loop is into the field, this disappears entirely because the current disappears entirely. So you only have the distance S to work from as it enters into this loop. Does that make sense? And you're not going to stop it because as the velocity decreases, the amount of EMF produced decreases. The reason I assumed we would choose this condition is so that our current is constant and our velocity remained constant at 2gs. If it was accelerating, none of this would work. Because if it were accelerating, then all of a sudden the amount of current would be changing the whole time, and you'd probably have to do some kind of calculus on this to figure out what was happening, which is why this condition makes the most sense for the kind of skills we have. I don't mean this mean. What I mean is we know this is the EMF. It has a sign in it because when we did our flux was based on a dot product, and the dot product had a cosine in it. So yeah, we took the derivative of that. I'm sorry, we had to leave the cosine in there because this became b s squared cosine of theta, which is omega t because theta is always changing. And we said that we were going to take the time rate derivative of this to get the EMF. I'm putting a lot out there and I'm writing really fast. I don't really know why, but let's just say that's what I have. No, not yet, but I'm not worried about that. What I'm saying to you is that once this thing is spinning, does it matter whether we have a cosine or a sine here? Okay, you're saying kinda, so...
Like, it's going to oscillate the same, but, like, they'll be their phase will be shifted.
I know, I'm trying to press you. You're a smart kid. What is the problem? Why is it important to know whether it's sine or cosine here? So let's understand the scope. Yes, sir.
When you will not have EMF induced at the exact moment where there will be no EMF before it switches to the opposite direction.
Right, it's going to be, what's the orientation of the loop when your EMF is maxed versus when our EMF is zero? That's the impression here. And that's what this tells you. That's why it's sine versus cosine, because either your EMF is maxed when the loop is like this, where it's pictured as now, or the EMF is maxed when it's turned 90 degrees. That's going to play a role in determining the torque, which is why it's worth talking about here. You understand why I'm bringing it up? You brought it up, and it's important. So when do we get the maximum EMF? When it's like this? Or when it's straight up and down? Two options. So this is the first option, right? This is based on the fact that at this moment right here, the cosine was 0. Right? This is what we're showing right now. I could have an option where I draw it a little bit to the side, where we are looking at a side view of that. And our square would be turned, so that's, like it's a line now. Mr. Shelton. I guess I could have left the squares the way they were. I don't know why I drew it to the side like that. But I did, so the original that's shown to the left is like this, and it is now turned 90 degrees. It has flipped. Because now that I'm here, which one of these, where is the EMF max? I guess that's what we're trying to figure out.
The max at the second one.
You're asking. You're smart kids. Tell me, don't ask me.
Max is at the second because D would be larger, right?
Well, my omega t has had to now advance to pi over 2. Right? And because we have flipped it 90 degrees. Seems to me that at time 0, the EMF would be 0, even though we have maximum flux. And apparently, when the time is advanced sufficiently for us to be at pi over 2, we now have maximum EMF, but that means that our loop has 0 flux. Correct? That's exactly what's being said here. Now, the EMF is not created because we have maximum flux or minimum flux. The EMF is created because of the rate of change of the flux, suggesting that at this moment, the rate of change is at its maximum. That's got to be what it means. And that must be what the derivative of sine and cosine is all about. That when cosine is at its minimum, when cosine is at 0, the rate of change is at its maximum. Doesn't that have to be the truth? Come on, you guys are all mathletes. Does anything of what I just said make sense to you? Because if it doesn't, I'll speak slower. I'm gonna draw a picture. Mr. Shelton's so good at it, so. Oh, I blew it. Right? That's what they look like? So, when the loop... can't put both on screen now because I was like that. When the loop is like that, this condition is right here. And this condition is pictured right here. Correct? I'm looking at two conditions, 0 and pi over 2. It seems to me that at time 0, when the loop is aligned with the magnetic field, I have maximum flux. But at that instantaneous moment, no EMF is produced. That's what the math tells me. Is that what the math tells you? Because the EMF is based on sine. Yes or no? I'm trying to see if your faces will reveal anything. Besides, I don't want to be here, Mr. Shelton. I should be gone like the other half of class. And I see that at pi over 2, it appears to me that the flux is 0. We have turned it so that no magnetic field passes through the loop, but the EMF is at a maximum. Which would also mean the current is going to be at a maximum. Bs squared omega over r sine omega t. So the current is a maximum when we're set up like that. Does that make sense? I'm just doing the math. Or trying to. I mean, in a few seconds, it'll be over here again. And when it does, it's going to look like this. Right? That's going to be when it sets back up to 0. And then this is going to represent this point. So I guess the question is, what torque are we fighting against and when are we fighting against it? It appears as though there won't be any torque when we're like this. There's no current in the loop. And we only get a torque when there's a current in the loop. We have to fight against that torque. We have to turn it. I would suspect that when there's a torque, we're having to apply a force in the opposite direction to get it to spin. I would bet that the direction of that current is to try and stop the loop from turning. Is this too much for you guys? I mean, just looking at the picture here, knowing the direction we're going to turn it, we're going to take it and it's going to turn with an axis like this. Okay? We all kind of imagine that for a moment with the spin direction up through its middle. Something like that. At this instantaneous moment, no torque should be required. If you don't remember, torque is torque arm, which is S over 2, times force, which in this case is going to be ISB, times the sine of the angle between those two. The torque arm is this way, and the force, well, there is none because there's no current right now. Yeah?
Do you have the force? Do you have to multiply by 2 to go the sides?
Well, yeah, there'll be 2 torques. But, I mean, because there's one on each side. But we also know that none of that really matters so much, right? Because right at this instant, there's no current. Now, when we reach this point here, we want to flip the other way. We know we have maximum current right now. So, we're looking at this from the standpoint of us flipping it, and I'm having a difficult time now with my drawing as I've written all over it. But our object has no flux passing through it, but our current is maximum. So how are we going to deal with how much torque is necessary? Well, the current's going, this is our bar, and our current's going to be going either this way, and we know that doesn't matter, this way into the board, or this way out of the board. That would matter. That's where we'd have to worry about it. But even still, oh wow. You're not going to believe this. Apparently my phone's been listening to me the entire time and has recorded all the things I said. I got like the longest text message. If I send this to Miss Casabank, she will flip out. So I have to find a way to delete it without sending it.
Don't fat finger it. What's that about?
I don't even know what to do. There we go, select all. Oh, it didn't select all. I'll have to figure that out later.
Philip. What did you fill out?
Oh wait, is the end of class? All right. I'm going to work on, because Oliver's got his hand up and he thinks I'm going to talk more about railguns, and I am not.